All right, welcome to Columbia Physics Preceptor TV. Today we're going to talk about standing waves. First of all, let's think about what a wave really is. You've all seen water waves, on the ocean. They're moving along. It looks kind of like they're moving, but really it's more of a transfer of energy than actually motion of actual particles. Usually I like to think of this as a wave in a stadium, and if you're in a football game and everyone does a wave, you don't really have people running around the stadium. Everyone kind of stands up and does their little part, and then they sit down again. So if you have some wave, it looks like the wave's actually moving, but really particles here are moving up and down, and over here up and down, so it looks like the wave is actually traveling. For a wave, we should define, in order to be able to talk about a wave, we need to have some definitions. Let's define what a wavelength is, first of all. A wavelength is a complete cycle of the wave. So let's start from here all the way over to here. This is one wavelength. We denote that by the letter lambda. So every time you see lambda, you should think wavelength. The other thing we should talk about is period. We're watching now a snapshot of a wave. In all reality, this wave is moving to the right. So if we're standing over here, it takes a certain amount of time for this point to travel all the way over here. The amount of time that takes is called a period. The time it takes for one wavelength to travel. We can also sit here and count for exactly 1 second, count how many wavelengths pass by. That's the frequency. And finally, or the two more things we need to discuss, the amplitude is the maximum height of this wave. So if we measure the height of the wave, this height here would be the amplitude. So I'm not going to write that down. That's just looking at the picture. The final thing is c. It's the speed of the wave. Now, some of these aren't independent. You'll see that the frequency and the period of the wave are actually inversely proportional to each other. You can imagine that if the period is 1/2 of a second, i.e. it takes half a second for an entire wavelength to pass, how many wavelengths would you count in 1 second? You'd count 2. It takes half a second for each wave to pass, so a full second would give you 2 waves. The units for frequency is hertz. It's the same thing as 1 per second. So it's 2 waves per second. If the period had been 1 second, well then of course if you measure how many waves pass through in 1 second, you'll find exactly 1. So in general, you see that the frequency can be obtained from the period by just taking 1 over the period. Or period is 1 over frequency, or if you want, frequency is 1 over period. So these two are actually related. Also, the speed of the wave can be determined from the frequency and the wavelength. So the speed of the wave is how much distance is traveled per time. Well, if I know the number of wavelengths that travel by per second, and I know the length of each wavelength, the amount of distance that the wave travels in 1 second is just the number of wavelengths f times the actual wavelength. So the speed here is actually lambda times f. And if you prefer, you can write f as 1 over the period, so you can write this as lambda over the period. Okay, so that's pretty much all the background knowledge we need in order to just understand waves. The next thing we're going to talk about is interference. So as of now, we've only discussed one wave. We always have one wave sitting here, and we define all these wavelengths and frequency. But what would happen if we have 2 waves moving towards each other? Let's say this is one big string, and one person sitting over here wiggling the string, and another person sitting over here and wiggling the string. Then, as soon as these two things meet, let's say this part of the string right here, this wave may be telling this part of the string to move up. However, this part of the wave, or this wave, might tell it to move down. In general, they don't have to agree. So this thing has to kind of compromise between these two waves, and kind of, let's say this one's telling it to move up a centimeter, this one's telling it to move down a centimeter, it won't move at all. However, if both of them are telling it to move up a centimeter, then it'll move up 2 centimeters. This is exactly what interference is. If they exactly cancel, it's called destructive interference. if they exactly add, it's called constructive interference. And in general, they don't have to exactly cancel or exactly add. They could be somewhere in the middle. This might tell it to move up a centimeter. This might tell it to move down half a centimeter. And in general, it will be somewhere in between. So this brings us to standing waves. Here we assume that the two waves were produced by two different people standing at each end of the string. Now, a more exotic thing can happen if you have the string tied to a wall. Just like sound waves, when you talk, create an echo, they come back, this wave incoming will actually create a reflective wave that's coming back. And as such, this scenario is very similar to the previous scenario where we had two different waves created by two different people approaching each other. So in general, if you have this moving up and down over here, you'll have some interference. And you've observed this. If you've tried to tie a piece of string to a wall, you can wiggle it up and down. You get all these really weird patterns. However, for specific if you wiggle this in exactly the right way, you can make these two waves exactly add and cancel each other in the right way as to produce a standing wave. And it looks kind of like this. It's enveloped by two different waves, and these points never move. And the wave always looks like this. It might have smaller amplitude, but it always is enveloped by this big wave-looking thing. So I'm sure you've seen this if you played with a rope, like attached to a wall. You can get all types of patterns in between here. There might be one big thing, or there might be two, or it might be four, like in this case, or any number of them, depending on how exactly you wiggle it. These points that stand still are called nodes. And these points that are exactly in between nodes, or the maximal displacement, are called antinodes. Also, we can notice that the wavelength here, this is a full cycle of the wave, from here all the way over to there. So in between those, there are two of these packets of standing wave. So in between two nodes is always half a wavelength. Half a wavelength here, half a wavelength here, half one here, and half one there. So they are a full two wavelengths in this standing wave. So the experiment we're going to do today is involving standing waves. The first part of the experiment, we're going to have a little machine wiggle a piece of string for us at exactly 60 hertz. And we're going to create different amounts of tension here. We're going to have this lay over a pulley and hang down here and be pulled down by a weight, some mass of mass m. And as such, we're going to, since we always have 60 hertz, we're going to get some type of standing waves in here. And we're going to measure the wavelength of these waves. So we're going to measure lambda. And from knowing lambda and the frequency, we can figure out what the speed of this wave is. Now, there's another way of figuring out what the speed of this wave is. Theoretically, this is the square root of the tension divided by mu. The mu here is mass per unit length. So what you should do is you should measure the length of the string, measure its mass, and then divide the two to get mu. Also, T here is a tension in the string. In this case, the tension is created by this mass m. It's pulling down. So the tension in this case is going to be mg. So you're going to have two ways of computing C. One is by measuring m and measuring the mass per unit length and computing C using this formula. And the other one is by actually measuring what the wavelength is in here and determining C from C is equal to lambda f. Two ways of determining it. So you're going to see that they may not exactly agree, but hopefully with an uncertainty they should. The second part of this experiment is about sound waves. So we're going to have a tube that's going to be partially filled with water, say up to some level here. This is all water. And there's going to be a little tube sticking out of here into a container of water. Now, by raising this up and down, you can increase or decrease the water level in here. Now, an important thing is in order to be able to do this, you have to be able to let air in here. Otherwise, there will be some pressure in here that prevents this water from exiting this container and entering the tube that you're using it for over here. So you all want to make sure to open the lid up here so that we can let the air come in. So, for various, we're going to have some type of tuning fork up here. We're going to create some sound waves, and we're going to let these go down into this tube. Now, because the air right next to this water level can't move, there has to be a node down here. Also up here, there's no constraint on how it can move, so there should be an antinode. So the simplest example would be an antinode up here and a node down there for standing waves. There are other examples when this might have another antinode in between, and there are, again, just like with a string, there are an infinite number of possibilities. Now, for a given frequency up here, there's going to be a certain wavelength that's allowed. So if we could measure the wavelength, we can actually find the speed of the wave. The way we're going to measure this wavelength is by having the tuning fork up here and raising the water level up and down. And as we do so, we're going to notice at a certain point, this sound wave gets amplified. And that happens when these are standing waves. So by doing that, we're going to be able to identify when these standing waves occur. So by measuring then, the first time it happens would be here, and the second time would be right here, and there are other times it would happen farther down. By measuring this distance here, and relating it to the wavelength of this wave, we can determine the C, because the frequency is given to us. It's either 512 Hertz or 1024 Hertz. There are two different tuning forks. One is 512 Hertz and one is 1024. So by performing this experiment, we're going to be able to determine the speed of sound in air. That's pretty much it. Good luck with the experiment.